Finish him. Kill the guy now. You have the gun. Beat him. What's wrong with you?
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have it last semester.
We by pounds on you. Very stupid though. We are changing that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
Hello, class. We are in this class to look at general topology, our first lecture in this series. Of course, in previous classes, we've discussed on what the concept of topology is all about. And the word topology emanates from the Greek word topo, which means points. And when we talk about general topology, we are looking at the point set topology. Of course, in earlier classes, we've seen what a topology is. But by way of review, I want to go through the concept before we go further into other things that the course entails. So let's take a look. Given a set X, okay? You can define a topology on a set as a class or family of sets, okay, denoted by this, is called the topology on X if the following axioms are satisfied. Let me call the first axiom T1. Empty set and X belong to the family of sets. By the way, let me state that this TOR X, which we regard as the topology, is a subset of the power set. Of course, you know that this set entails the family of all subsets, of X. And that will include the empty set, X, and all other subsets of X. So the second axiom, which a topology must satisfy, is that the arbitrary union for some I in an indexing set, we can have, let me call them UIs, which belong to TOR X, so that their union also, the union of all the UIs there, also belong to TOR X. So we call this arbitrary union. And then the third axiom that must be satisfied is what we call the axiom of finite intersection. So for I equals 1 up to n, a finite intersection of all the ui's in Tor X is also satisfied. So for a finite number of sets ui, we can have a finite intersection of those sets. Now, each of these sets that belong to Tor X, every member in Tor X is called the open set. So we know that every element in Tor X is an open set. So we need to note here that elements in Tor X themselves are sets, since we said Tor X is a family of sets. So that means in this case, an empty set is an open set. X is an open set. All the other subsets of X which form the members of Tor X are also open sets. And looking at this, we need to know that, so if every element of X is an open set, that means all the ui's are belonging to Tor X are open. So if we can define open sets, we should also be able to define closed sets. Closed sets in this case are actually the complement, relative complement of every open set. So a set is said to be closed if you can find an open set so that, or let me put it this way, a set X take away that open set is closed if the open set ui belong to what? Tor X. And we have a very amazing quality in the set of topology, because you will observe that empty set as well as X can be what? Open and at the same time closed. So let's see, for instance, empty set is closed because an empty set is equal to X. The open set in this case is X. X take away X is empty. Likewise, we can also say that X is closed because X is equal to X, which is the set we are considering. Take away empty set. And we know that X is open. When X is open, the empty set is closed. When empty set is open, X is closed. So we see there that empty set and X share these two description of being open and closed. And when a set is open and closed, we say that set is a clopon set. When a set is open and closed, it is said to be a clopon set. So that takes care of that. So that means that both X and empty set are closed and open. So empty set and X are therefore clopon sets. Okay, so having talked about that, the next thing we want to look at here is the types of topology. I'll just refresh our minds about the types of topology we have. Of course, we know we have the smallest topology called the trivial topology. And the trivial topology here is made up of both the empty set and X itself. So the trivial topology, which I call tor naught here, is actually made up of empty set as well as X. Now, if you observe very well, you will notice that this trivial topology satisfies all the axioms of a topology. Number one, we see that both empty set and X belong to that set. That is satisfied. Number two, we see that if we take the union of the sets inside this class of trivial topology, which is empty set, union X, what we obtain is X. If, on the other hand, we take an X belong to where? That trivial topology. If we take the intersection of the empty set and X, what we get is an empty set. And this still, so it satisfies both the arbitrary union as well as the intersection, the finite intersection. So here we see that the trivial topology satisfies. Now the largest kind of topology is called the discrete topology. And the discrete topology occurs when tor of X is equals to the power set. So, discrete topology. This is simply any topology on a set X which is equals to the power set of X. Of course, you will notice that every element in X here will get a singleton. Okay? For instance, if you had a situation where X is equals to the triple ABC, of course, you know the power set of X will be made up of empty set X itself. It will be made up of singleton A, singleton B, singleton C, then the duple AB, BC, and AC. So this is the power set of X, and it's made up of how many elements? 8, okay? Which is the cardinality of 2 raised to power, the cardinality of X, which is 3. So if you count 1, 2, 3, 4, 5, 6, 7, 8, you have 8 elements in the power set of X. Of course, you see the characteristics or the feature of topology expressly and explicitly appearing here. Of course, you can see empty set and X, which is the first axiom of a topology, exists here. Then followed by Then we have, you can take the union of all these singleton and take the union of everything here. You will still get the set here, which is x. You can as well take intersection of a finite number of them. You will always find the element inside that set. So we see here that discrete topology satisfies all the axioms of topology. So we've seen the smallest as well as the biggest form of topology expressed there. We have other forms of topology, such as closed topology, or what we call the cofinite topology. Well, of course, you have seen in previous classes what was described as the finite closed topology, or cofinite topology. So, cofinite topology. Of course, the cofinite topology is a class of topology on X, defined by a set of open sets. This is open sets. I can decide to call it UJ here, belonging to the what? The power set of X, such that the number or the cardinality, the number of elements in X, take away UJ, is finite. Now, we notice here that the number of elements here is finite. That's one. Number two, we notice here that this is a closed set, because when you take away an open set from X, what you get is what? Is a closed set. So it's finite closed topology. So it shares the two. So that's why we call it cofinite topology. Now, the next thing we've talked about in time past are both the finite segment and the initial segment and the final segment topology, which I may not have the time to really talk about. But before we go ahead, well, let me talk about it. Let's talk about initial segment. Initial segment topology. This kind of topology is a topology defined on the set of integers, basically positive integers. So in this case, X is a set of natural numbers or positive integers. Of course, you know, if you want to define a set, you can have a set X or of natural, let me call it a subset of this set, a subset of X, in this case where X is that, so that I will call this one S naught, and then I will call the final set here, I will call it SF, where S naught is made up of 1, 2, up to n elements. Then the final part of it is made up of n plus 1. So we see this one, the final segment is infinite, but the initial segment is what? Finite. So if you want to define any topology on these two, what you are going to have is going to be what we call both the final as well as the initial segment topology. So in this case, you can decide to have this. This topology is dependent on the what? Initial segment. So we call this one initial segment topology. I'll write that for short. And the final segment, I call this the final segment topology. So that takes care of that. Then another type of topology which is commonly used in analysis is what we call the quotient topology. Quotient topology. Quotient topology. Now, when we talk about quotient topology, it is not just dependent on X, but it's dependent on a map. So, we call this a topology dependent on a map, which is defined by V. Here, V is an open set. It's a subset of Y, where we can have the inverse of the map belonging to the topology over X, okay? And this, I'm using a square bracket because this is a map over a set. It's a subset of X. Now here, F is actually a map from X to Y. So, for a quotient topology to exist, there must be a map taking X to Y. And when you want to take the inverse of this map, the inverse of the map will reverse the map. So it will go from Y to X. So that is why the choice of the open set here is V. It's a subset of Y. And this inverse map acts on the V here, which is a subset of Y. And when it acts on it, it is found inside X. So an X is a subset or is an element of its topology. So, of course, the inverse map of this, sorry, this should be a square bracket, will belong to the topology of X, where the inverse map here is subset of X. So that is quotient topology. By this, we've at least summarized what we've done so far. I'll just introduce you to the concept of accumulation points. Accumulation points refer to points, converging points of all other points. And it has other names such as cluster points, limit points, which we are going to use interchangeably. Of course, unlike when you were doing elementary set theory, you take an element in a set to be called a member of a set. But when you come to topology, every element of a set is regarded as a point. Every element of a set is regarded as a point. So, in particular, we will be concerned with points and will relate them to sets. Now, so we look at accumulation points. Accumulation points. Okay. Now, let X be a set. Of course, we know. Let X be a topological space. We can use it. A topological space. Okay? So, by this, we mean that X is same as X to X. Because X is not just occurring, you can define a topology on it. So let X be a topological space and let U be an open set. Let U be an open set. In other words, that means U is a member of the topology on X. Now, if you have a point, okay, let P be a point in A, which is a subset of X. Let P be a member of A point in A, which is a subset of X. Now the limit points of A is regarded as the cluster point or the accumulation point. So then P is regarded as an accumulation or cluster or limit point of A if we take the intersection of A and an open set in Tor, and we take away a point P from that open set. If this is not empty, then P is a cluster point. Let me make an illustration here. Let me make an illustration here. You have a space, let's call this X. And right inside X, you have another set which we call A. And right inside A, you have a point which we call P. Okay. Now, if you have a point P in A, and then we say that U here is an open set of Tor X. Of course, you should expect X is an open set. You can also have other, I'm going to use broken lines to indicate open. So, let's say we have an open set here. Okay? It can contain A or it can just intersect A, whichever. But what we know is that that open set must contain a P. Now, by the time you take away P from this open set. If you take away P from open set, that is, you take away the singleton P. After taking away P from this open set, if you have other points left inside A, then A intersect this is not empty. But if by the time you remove P from the setting, you don't have anything left, then we call P an isolation point. Okay, let me make an analogy. I will make an analogy. We have a class made up of students. Let's assume an arbitrary number of students. And we decide to pick that one student out of that class. By the time we pick a student out of that class, if we still have all other students present in that class, that means that that class did not contain only one student. There are still other students. And so that student that we just picked out is an accumulation point. But if by the time we take a student out, we have no one left, it means all the while that student was the only isolated point in the class. And so that is the idea of isolation points. Now these, we've described three things here, or two things in particular: accumulation point, which otherwise is called cluster point, and isolation point, using this diagram. Now, when you have a collection of accumulation points is what we call the derived set of A. So we say the derived set of a set A is given by A prime. Now, let me make a very important note of warning here, because a lot of students confuse symbols in mathematics. In some mathematics class, A prime, people use it to mean complement of a set. In this course, A prime is never a complement of a set, but rather a derived set of A. Now, let me tell you what that means. This is defined as the collection of points such that this happens, such that A intersect, you take away the singleton set P, is not empty. Therefore, we say that A prime is a collection of all the limit points, all the accumulation points of A. Let me give you a simple example. Let's assume a set here is just what we call the Clopin interval. The Clopin interval. Or the open interval. We can make it an open interval, okay? Now let's assume we want to define the limit points. What are the limit points of this open interval? The limit points of this open interval is to the left 0, to the right is 1. So we have what we call our A prime to be what? 0 and 1. So when you draw a line and you have your 0 and 1 point on the number line, you have this open interval here. We leave it unshaded because it is open. Now, the limit points here are 0 and 1. So, when you now take the union of A and A prime, what you have is what we call the closure of A. The union of all the limit points of A and A is the closure of A. Let's look at it. What if we are now to put, because this open interval excludes 0 and excludes 1. By the time you put 0 in it and you put 1 in it, what happens? You have what we call a closed interval. And this is simply what we call the closed interval 0, 1. Of course, if you want to express this, it simply means all the set X such that X is greater than 0, it's not equal to 0, and X is less than 1. But in this case, this simply means the set of points X such that 0 is less or equals to x, and x is less or equals to 1. So we have closed it simply by this definition. So this is called the closure of A. Other notations for this is CL, A, closure of A. Now, we need to also understand the importance of these notations. Now, I need to also tell you something associated with points of A, which we are going to talk about, which is the interior. Let me talk about the interior of a set. The interior of a set. Let X be a topological space. Let X be a topological space. A point and U belong to the topology of X. A point, or let me call it rather than a point, let's define the interior. The interior of a set A, which is a subset of X, is given or is defined by this notation. This is how we denote it. We denote it as this interior of A, or A with a 0 on top. This is defined as the largest open set contained in A. The largest open set contained in A. And we can define it as the union of all open sets contained in A, so that U is an open set. Now, what do we mean? You have a set X here. You have a set X here, and we have another set A here. Now, you can have a small open set here. Let me call it U1. You can have a larger open set here. Let me call it U2. If you continue to increase the large open set and it does not go out of A, you continue to enlarge the open set and it doesn't go out of A. How do you obtain that? By just taking the union of them all. When you take the union, what you will get will be the largest open set containing A. So when you do that, what do you have? You have the interior of A. The interior of A cannot be equals to A, but it must be inside A. Okay? Now, you can also have the boundary of A. This is a classroom. When you have a classroom, you have the walls of the classroom. As much space the largest space you can have inside the classroom is the interior of the classroom. By the time you are talking about the boundaries, you are now talking about the boundaries, then you are talking about something else. Now, that is the interior of A. We can also have what we call the closure of A. The closure of A. The closure of A of A, on the other hand, is just the intersection of closed sets that contain A, where this closed set is X, take away the open set, and the open set, of course we know, is a member. So the definition of closure of A here is different from that of interior because it's the opposite of what we used to have. Okay. I think I have 5 minutes to round up. Thank you. Now we have this to be the smallest closed set that contains A. The smallest closed set that contains A. So it's not the interior now, it's the enclosure. You have an egg. In the egg, you have a yolk. In the yolk, you also, with the yolk is contained inside the liquid part of the egg. And then you have the shell that is the enclosure. That is the smallest restriction of space that the egg is found in. So you are talking about closure here. So the closure of a set is what you have there. Now, apart from, and I've told you another definition for closure is this, the union of a set with its limit point. So you can define it interchangeably depending on what you want to do. Now, this derived set, you can also define it mathematically as derived set of A as the closure of A, take away the interior of A. The closure of A, which is the boundary of A, and take away the interior from it. What you have is the shell. And that shell is the limit, is the set containing the limit point. Now, that same shell is what we call the boundary. Now, the boundary or the frontier, as they may be called interchangeably, the boundary of a set A is given by the partial D of A. Okay? Can also denote it as BD of A. The boundary of A is given as the intersection, the meeting point between the closure of A and the closure of X take away A. This is what we call the boundary of A. And this are equivalent to each other. Then we also have what we call the exterior of A. If we have the interior of A, we should also be able to define what the exterior of A is. The exterior of A is given by EXT, then you have A there, is given by the closure or the interior, let me call it, the interior of X take away A. The interior of X take away A. Let me illustrate it diagrammatically. If you have a set, let's call that set X, and you have a set A in X. By the time you take away A from X, what do you have? You have the exterior. So now, when we now talk about the exterior of A, we are now talking of the interior. This, when you remove this, we are left with X take away A. Now, the interior the interior of x take away A is the exterior of A. That talks about all the points outside A here. So, by this now, we've been able to resolve some elementary concepts in topology, which describes accumulation point, derived sets, interior point, isolation point, boundary point, and exterior point of A. Thank you.
Finish him. Kill the guy now. You have to go. Beat him.
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
So it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting for in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have you last semester.
We pounce on you. Very stupid. Oh, yeah, change that section to ACTV right now. And oh God, the baby was what you was born. Stupid boy.